Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at the three-dimensional structure of molecules. If you want to, feel free to do some yoga along the way. In this case, just think about each of your limbs as a different adjoining molecule and your body as a central molecule in the structure, and you'll do fine. So when dealing with molecules, one of the important things to remember is that the world isn't flat, neither are molecules. So everything is going to have a three-dimensional shape to it. And we've got several different shapes to choose from. Now, when doing this, what we're going to do is use what's called valence shell electron repulsion theory. This is more commonly known as VSEPR. I know that's not how it's spelled. And what it can be done is used to predict the structure of electrons around a central atom. This is called the electron geometry. So when we do this, we're going to start by essentially counting the number of bonds and low pairs around the central atom. If I've got a double bond, this is still going to only count as a single group of electrons. And then what we do is think about all of those groups of electrons, whether they're a pair of electrons in a lone pair or a pair of electrons in our bond, hate each other. And we're going to assume they want to be as desperately far away from each other as possible. And when we do this, we're going to have a certain number of structures that are going to be possible. And we're going to represent their three-dimensional nature with dashes and wedges. So if you see a wedge, it means that the group is coming forward. And if you see a dashed arrow, this means that that group is pointing backwards. And as a result, most of our geometries are going to tend to adopt one of 5 key electron geometries. So if I only have 2 substituents, this is going to be linear because those 2 groups are going to want to be as far away from each other as possible. If you have 3 substituents, then they're going, in order to be as far away from each other as possible, they all have to be equidistant in a plane. That way, they stay all very far away from each other. Now, as soon as you have, and this gives a trigonal planar, 3 groups in a plane, fairly straightforward. Now, if we have 4 groups, now we need to essentially bring in an extra dimension because the only place where there's space to add another group is up. So we have one group essentially at the top of my triangle, and this makes a tetrahedral geometry. 4 substituents, tetrahedral. Now, if I'm going to put a 5th group on there, in order for everyone to stay far away from each other, it has to come in from the bottom. And now I've got still a trigonal structure, but I now have essentially 2 pyramids, one pointed up and one pointed down. So trigonal bipyramidal. And then if I need to put in an extra group, only place it's space is to come in and push 2 other groups out of the way on the sides. This gives me an octahedral where everybody's separated by 90 degrees. Now, these configurations are going to be our electronic geometries, and let's go ahead and look at how we can determine a couple of these. So if I've got CO2, it's got 2 bonds. Doesn't matter if they're single or double bond. A bond is a bond. So this gives 2 groups of electrons. So in order for them to stay as far away from each other as possible, they have to adopt a linear electron configuration. Then we have ozone, which we've encountered before. It's got 1 double bond, 1 single bond, and 1 lone pair. So this is 3 groups of electrons. In order to stay as far away from each other as possible, we get that trigonal planar structure. Now let's go to ammonia. In this case, I've got 3 single bonds, 1 to each of my hydrogens, and I have this left behind lone pair. So this gives me 4 different places my electrons are pointing. Only way to adopt this is to get this tetrahedral structure. So it's essentially a pyramid with an extra group pointed right up top with a funny little hat. And then if we go to phosphorus pentachloride, this has essentially 5 single bonds, each pointing in a different direction. This gives us 5 different groups of electrons. They have to adopt this trigonal bipyramidal structure. And finally, we have an odd case of one of the rare cases of a noble gas forming a complex structure. as xenon can actually be mugged for a couple electrons by the world's most electronegative atom, fluorine, to generate xenon tetrafluoride. And this has 4 single bonds and 2 lone pairs. Now, in this case, this gives us 6 electron domains, and thus octahedral. So a good way to think about it is the fluorines are going to stay as far away from each other as possible, and I'll have 1 pair of electrons pointed up and 1 pair of electrons pointed down. And these are more or less our 5 classic electronic geometries. Everybody's going to adopt one of these 5. There is notably a 6 that you may encounter, and that's another form of linear if you only have 1 electron domain. But pretty much the only species you'll see adopt that regularly is hydrogen, and it's linear, so we don't really care. But it is worth noting it's out there. Now, one of the important things to remember is that this just tells us about where the electrons are pointed at. But most of the time when I'm dealing with molecules and molecular geometries, I care much more about where the atoms are pointed rather than the electrons. So we have a different type of geometry which we use, which is called, not too surprisingly, our molecular structure or geometries. So what this does is it essentially ignores any lone pairs, because if I'm going to go ahead and observe the structure, none of those lone pairs will be present. So if I go ahead and do an X-ray, I'm not going to see the lone pairs or only see the atoms. So a good way to try and figure out what our structure looks like is you're going to first want to figure out what your electronic domain is, how many electron domains you have, 2, 3, 4, 5, or 6. And then you need to figure out how many lone pairs you have. So let's say you've got 2 different groups. Let's say you have 2 different electron domains. Now, this means you're going to be linear. It doesn't matter even if you do have a lone pair, because guess what? You'll still be linear. However, let's say I have 3 different electron domains. Now, if each of those is a group, a different atom, then I will be trigonal planar, because whenever your lone pairs equal your number, whenever your electron domains equal your number of atoms, what you see is what you get, and your molecular structure will be the same as your electronic structure. However, let's say I have something like ozone, which has a lone pair instead of another atom. Well, at this point, I don't see that lone pair, and all I see is these 2 different atoms, and it forms this bent structure. And if I have 2 lone pairs, well, then congratulations, I'm still linear because I'm only seeing this 1 coordination. Now, what happens if I've got 4 electronic domains? Then, if I have no lone pairs, my molecular structure is my electronic structure, I'm tetrahedral. If I only have, however, if I have 1 lone pair and I only have 3 different adjoining atoms, then, well, I don't see this top part, and so I still have this trigonal structure, but it isn't planar. It actually has an angle, so we call this trigonal pyramidal or trigonal pyramidal. Because I have a triangle that's a pyramid. Ta-da! However, if I have 2 lone pairs, so I only have 2 adjoining atoms, congratulations, I'm bent. Now, one of the important things to note, if I say my molecular structure is bent, this doesn't mean a lot about my angle, because you can get a bent structure from either from having 4 electron domains or 2 electron domains. But you get a very important difference. If I have 3 electron domains, my atoms are going to be 120 degrees separate from each other. But if I have 4, these extra electrons have pushed my 2 atoms closer together, so you'll be separated by 109 degrees. And this is actually one way that we can use a molecular structure to figure out how many lone pairs are present in a system. Now, especially when we're dealing with metal centers, or heavy atoms like phosphorus or sulfur, it's possible to have 5 electronic domains. And if we have no lone pairs, our molecular structure is our electronic structure. We are trigonal bipyramidal. However, if we have 1 lone pair, we make something called a seesaw shape. So This is one of my favorites. It looks like a person. You've got 2 legs and 2 arms that are held out. One of the reasons it's called seesaw is because you can think about these as the post where you put down the seesaw, and this is the bar that moves backwards and forwards, because it can be, these 2 X groups are often separated from each other by 120 degrees or 180 degrees or very close to. However, if I've got 2 lone pairs, then these lone pairs tend to be close to each other, and what results is a T shape in between the 3 different structures. And if I've got 3 lone pairs, these 2 atoms want to be as far away from each other as possible, and I've got another linear structure. If I have 6 electron domains, I can get an octahedral, a square pyramidal, a square planar, a T shape again with very similar angles as from the 5 electron domain structure, or again, a linear structure. And I do want to emphasize that if we have 2 substituents, no matter how many lone pairs, we're either going to be linear or bent, because this is going to be the way that 2 atoms can be as far away from each other as possible. Now, one of the things I do want to emphasize is the angles presented here are kind of the idealized angles. And it's important to realize that our lone pairs are going to occupy slightly less space than a bond. And this can cause some mild distortions from these idealized geometries. So let's take a look at a bent molecule. So if my adjoining substituents are fairly big, they're going to want to push away from each other as hard as possible. So this angle can be a lot larger than that 120-degree angle, because they'll push away from each other, and they'll push away from each other way more than the lone pair will push back on both of them. And this will hold for most of these modified molecular geometries. So, gave you a lot of information to memorize. Now let's go ahead and try and put some of this to practice. First of all, let's say I want you to construct a 3-dimensional molecular structure. How are you going to do it? The first step is, as always, going to be drawing a Lewis structure. Then once you have your Lewis structure, count up the number of electronic domains, include the number of bonds, include the number of lone pairs. You can use this to determine your electronic geometry. Once you have that, figure out how many of those electrons are lone pairs, subtract out, and you should be left with your molecular geometry. And again, always worth noting, if you have no lone pairs, your electronic geometry and molecular geometry are always going to be the same thing. So let's put this into use with a couple quick examples. So let's go back to CO2. In this case, I've got 2 electronic domains and no lone pairs. So my electronic geometry is linear, my molecular geometry is linear. Let's take a look at ozone. My electronic geometry is trigonal planar, but since I have 1 lone pair, I've got a bent molecular geometry. Let's go back to ammonia. It has a tetrahedral electronic geometry, but since I have 1 lone pair, this leaves me with a trigonal pyramidal molecular structure. And for phosphorus pentachloride, electronic geometry is trigonal bipyramidal. No lone pairs, we have a trigonal bipyramidal structure. And let's go ahead and finish off with that fun xenon structure. Octahedral electronic geometry, 2 lone pairs, will ensure that all 4 of these fluorines are pointed as far away from each other as possible. It should be square planar. Now that we have these structures, why on earth do I care? And we're going to be talking about this next time as we look at some of the consequences of these 3-dimensional structures and what effects they'll have on the real world. Until then, take care.